during my PhD. Coming to the topic of presentation, the topic of today's presentation is tunable bandpass filters for communication systems. Much of this work was carried out during my PhD time in University of Waterloo, Canada, under the supervision of Professor Rafat Mansur. I will skip this slide because Abdullah has already introduced me to you. We covered almost all the points that I had in this slide. The only point is this is how I look like. Okay, the flow of this presentation is as follows. I will give you a very brief introduction about the research motivation as to why we started this work. And followed by literature survey. We did an exhaustive literature survey and I will be discussing that as well. Then I will present two technologies in waveguide and coaxial, tunable filters in waveguide and coaxial technologies. Some of the innovative structures that we came across, innovative configurations that we came across. Finally, conclusion and presentation. Please feel free to stop me if I'm going fast, and you can take the liberty to ask any doubts or any clarifications at any point during the presentation.
And just to add one more point, sorry to interrupt. So I request all the participants, please unmute them, please mute themselves, okay, throughout the talk. If you would like to have any questions or if you'd like to ask any questions, please feel free to ask, okay? Because we are recording the session, so any background noise will be very difficult for us, okay? Thank you. Please go on. Sorry to interrupt, Dr. Gowrish.
Thank you, Professor. So coming to the research motivation, one of the applications of tunable filters is satellite communication application. As we all know, the life of a typical communication satellite presently is around 10 to 15 years. So this is the life of a typical communication satellite. This is not because of the electronics. The electronics life is much longer than this. This is mainly because of the exhaustion of the chemical propellant that is used for orbit correction and orbit raising. So the satellite industry is ambitiously working to enhance the life of a communication satellite from 10 to 15 years to double it. That is around 30 years. So that is what the satellite industry is ambitiously working towards. And how are they working towards that? There are two approaches which are being extensively being researched and developed. The approach one is using electric propulsion system for orbit rising and station keeping. And the second approach is robotic refueling, where the chemical propellant will be refueled using another space orbit, satellite. For example, is this science fiction? No, this is happening as we are speaking. For example, the Airbus SES-12 and SES-14 missions already incorporate electric propulsion system in their communication satellite. And this was launched in 2018. This was 5 years ago. And NASA and Orbit Fab have already demonstrated robotic refueling of chemical fuel in International Space Station in 2019. So it is very much possible that within a decade or so, the life of a typical satellite, communication satellite, will be around 30 years. This will force all the electronic engineers to have reconfigurable radio or a flexible radio, as it is called. Sometimes it's called on-orbit flexible payload. So it requires reconfigurability in frequency. It requires reconfigurability in the bandwidth, radiation coverage, and radiated RF power. What we are focusing on is reconfigurability in frequency and bandwidth. So this is one application for tunable radios or tunable filters as such. The second application is base station application. As we all know, there is exponential trend in the data usage thanks to multimedia technology and its revolution. This has tremendously increased the way we are using the data. This leads to an expensive affair of installing remote radio units or antenna integrated units. For example, if you take a LTE site deployment cost, around 24% of it goes into the real estate and 23% of it goes into the civil works and 13% of it goes into the new radio, antenna feed or the new radio. So if we have a reconfigurable radio or a tunable radio, then we can significantly reduce this cost. and that will reduce the prices at which the data can be shared with the users. So this is another application of tunable radio or the configurable radio. So having looked at the motivation for working on tunable radios, let us now look at a typical architecture for a reconfigurable radio. So the tunable radio would include in the transmitter side a power amplifier on the front end, the power amplifier, bandpass filter, and an antenna. And on the receiver side, it would require antenna, bandpass filter, low noise amplifier, mixers, and local oscillator. And we are all aware of that the power amplifier, antennas, low noise amplifier, and mixers are all wideband components. So there is no challenge there when it comes to designing, when it comes to the bandwidth. Whereas the two key narrowband components are the local oscillator and the bandpass filter, the front-end bandpass filter. And we are also aware that the local oscillator is easily reconfigured using PLL architecture. Thanks to PLL architecture, the local oscillator can be easily reconfigured over a very wide frequency range. So the bottleneck for tunable radios, successful implementation of a tunable radio is a tunable bandpass filter. So the way we are approaching is we understood why the tunable radios are essential in the upcoming days. And the bottleneck for the implementation of the tunable radio is basically tunable bandpass filter, which most of the people don't recognize it. So this component is a real bottleneck or the
Hello, Gowrish sir.
Yes, Gowrish, some problem maybe.
Yeah, it's my side, it's my end. Am I audible, sir?
Yes, you are audible.
So I will share the screen.
Yes.
Is it visible?
Yes.
Okay. Sorry for the disturbance. It was at my end. So the way we are developing the story is the tunable radios becomes extremely important in the decade to come. And in the tunable radio, the bottleneck for successful implementation of a tunable radio is basically a bandpass filter, tunable bandpass filter, because all other components of a tunable radio are either wideband or they can easily be reconfigured. So that's why we were focusing on the tunable bandpass filters in our research problem. So we made an exhaustive literature survey. What were we focusing on when we were doing the literature survey? We were focusing on the high quality factor tunable radios, tunable bandpass filters, because the insertion loss has to be low. The frequency tuning range should be around 15%, higher the better. But we were focusing on what was available in the market, which was around 15%. Absolute bandwidth has to be remained constant over the tuning range. This is extremely important because we know that the data rate is directly proportional to the bandwidth, and the rejection criteria can be met only if the bandwidth is maintained constant over the tuning range. So this is a very key criteria or the requirement for tunable bandpass filters. And the most important and the least neglected of the feature is the number of tuning elements should be minimum possible. Ideally one. We will understand why it is so. So these were the different specifications that we were looking at while doing the literature survey. And it is important to note that since we were focusing on high quality factor bandpass filters, they are all mechanically tuned. As we were focusing on vector based tuning, because as soon as we introduce a vector, it degrades the Q factor of the resonator significantly. And it is not much of usage when it comes to base station application or the satellite application. Hence, we were focusing on mechanically tuned bandpass filters using a motor, piezo motor, or a magnetic motor, or using MEMS. So we made quite exhaustive literature survey, and we found out that none of the available open literature or the product available in the market were meeting the desired specifications, as you can see in this table. Then some of you may think that what is the big deal in this? For example, if you introduce a tuning element to each of the resonator and the interresonator coupling, then you can actually transform any bandpass filter into a tunable bandpass filter, right? So you take an nth order bandpass filter that has 2n+1 independent variables, including the resonators and the coupling between the resonators. So if you introduce so many motors, 2n+1 motors for a fourth order filter, that would be 9 motors, then that becomes a tunable bandpass filter. So it's as simple as that. But it's not as easy as that. Because remember, we are trying to minimize the number of tuning elements. And I will come to it why we want a single tuning element. So people, it's good for publication, but none of the products come out in the market with such large number of tuning elements. So researchers at University of Waterloo did exhaustive research on this, and they tried to reduce the number of tuning elements from 2n+1 to n. That is 50% reduction of the tuning elements in 2013. This is a big step. This was a pretty big step. So basically what they did was they removed the tuning elements between the interresonator couplings, and they introduced tuning only for the resonators. So you can see 6 motors here, right? This is a 6th order filter. And there are 6 motors, and these motors go up and down. The tuning plate goes up and down and reconfigures the filter response. You can see it on the left side here. Basically, the plate is moved up and down with the help of piezo motors. So this was a big step, and there were a lot of industries approached them. For example, Huawei approached them to make tunable bandpass filters for their base station applications. And there was also a satellite industry which was interested in getting this for their on-orbit flexible radio in 2013, remember. Then in the practice, when they actually want to build a control system for this, it becomes extremely difficult, extremely challenging to control these 6 motors and still maintain the same response. So that practical challenge was blocking this idea from going into the literature to the product. So when I joined the University of Waterloo, we asked ourselves, can we further reduce this to a single tuning element? That would be revolutionary, because then you have a single motor, you rotate the motor, and the frequency response tunes. So the control system design is extremely simplified. So that's the reason why single tuning element is a goal, and it is hard to do it. So when it comes to bandwidth reconfigurable bandpass filter, there is even less reported literature, and there is a lot of scope for implementing such filters. For example, the filter developed here is by European Space Agency in collaboration with one of the universities, top universities in the Europe. And they have developed a 4th order bandpass filter, bandwidth reconfigurable filter. But look at the number of tuning elements. There are 9 tuning elements in this filter. So there would be 9, the control system is extremely complicated. So this is an open problem even today. So what is the challenge? The challenge is to develop tunable bandpass filters with minimum number of tuning elements. I'm stressing that again and again. Ideally a single tuning element, while maintaining high performance, while maintaining all the desired parameters like constant absolute bandwidth, high Q. So these are the desired parameters. The single tuning element has many benefits, especially in the space application, because it enhances the reliability. It significantly eases the complexity of the tuning control system. And of course, there is the added benefits of reduced cost and size as well. So in waveguide technology, I will be presenting 3 tunable filters we have developed. One using a single tuning element, all pole filter, single tuning element with transmission zeros, and a bandwidth reconfigurable filter. So what is the theory behind this, or the design procedure behind designing such tunable filters? It is very simple. Okay, it's extremely simple. There are only 2 equations, mathematical equations. And if we satisfy those 2 equations, the filter design can be almost automated. So we start with the specifications, and we design the interresonator coupling. We design the input-output coupling, finally resonator loading, and we do the filter optimization. Any of the optimization techniques can be used. We use space mapping optimization because it is much more powerful than any of the other optimization techniques. So for the inter-resonator coupling, we have there is two criteria, one for the inter-resonator coupling and one for the input-output coupling. So for the inter-resonator coupling, the product of the physical coupling coefficient and the resonance frequency has to be constant for maintaining the constant bandwidth. Because the bandwidth has to be constant, that is the requirement, and the normalized coupling coefficient doesn't depend on the bandwidth. Therefore, the product of the physical coupling coefficient and the resonance frequency has to be constant over the tuning range. And for the input-output coupling, the reflection group delay has to be constant. So if we maintain these two criteria, then the design is straightforward. So let me come to the first idea. So the first idea is, how do we tune the filter? So the idea is we use the TE101 mode, the fundamental resonant mode within the rectangular waveguide cavity. And we know that if we change the A dimension of the waveguide by moving a wall, if we linearly displace the one of the side walls, the A dimension changes, and that changes the resonance frequency of the fundamental resonating mode. So this is the idea behind tuning the filter. Basically, we are linearly displacing the side wall of the waveguide. So we used a single septum for inter-resonator coupling, and we found out that the product of the physical coupling coefficient and the resonance frequency was not constant. Remember, we saw that it has to be constant for achieving the constant bandwidth. Since it was not giving us a constant value, we went into the double septum. Because double septum has many parameters like position of the septum, the length of the septum, the spacing between the septum. So there are multiple degrees of freedom. And we found out that the double septum filter, the double septum inter-resonator coupling gives us the constant bandwidth over a very wide tuning range. From 14 gigahertz to around 18.5 gigahertz, it gives us a constant bandwidth criterion can be achieved. So we use the double septum filter. Inter-resonator coupling, sorry. So when it comes to input-output coupling, we used a simple probe. So it has 3 degrees of freedom, the length of the probe and the distance of the probe and the position of the probe. And we were able to meet the constant absolute bandwidth criterion, that is the reflection group delay has to be constant. We saw that, right? So the reflection group delay should be constant because the right-hand side in this equation is constant for the constant bandwidth. So the reflection group delay, S11 group delay has to be constant. So the reflection group delay was constant, reasonably constant over the tuning range. So we adopted the probe coupling. So what was the next step? So the next step was to incorporate the inter-resonator coupling and the input-output coupling and design the filter. Then, wow, we faced the problem of spurious once we designed the filter. So the desired frequency, operating frequency was 15 gigahertz, whereas there was a spurious at around 12 gigahertz, the first spurious, and there were so many other spuriouses. So what we did was we shaped this tuning wall or the linear displacement wall. We shaped it from the simple rectangular wall. We shaped it into the a square, and we gave a cut at the ends of the resonators. This actually pushed the spurious well beyond the desired frequency band. So we were able to solve the spurious problem. So we integrated the inter-resonator coupling using the double septum, input-output coupling using the probe, and the tuning element, which was shaped now instead of a simple rectangular slab. We gave an air gap on the top and the bottom around 0.25 mm. So, because there should be friction-free movement. So we used Kapton tape on the top side and the bottom side for friction-free movement of the tuning element. And these are the simulated response. You see a very neat response of the filter being tuned using a single motor. So basically there is a linear displacement of the tuning wall, and then that shifts the frequency response from 14.5 gigahertz to around 17 gigahertz. And the return loss performance is also reasonably good, better than 15 dB approximately. So we were able to meet the constant bandwidth criterion requirement. It has to come, right? Because we ensured that there was a constant bandwidth criterion with the double septum. We ensured here. And the bandwidth variation was less. The tuning range was around 15%. And the insertion loss was also pretty good, around 0.3 dB over the tuning range. So we build the filter. So the next step, the logical step is to fabricate this. For the proof of concept, we fabricate this filter using copper and aluminum. And these are the different parts I have shown here. There was already a tuning station that one of the students had built there using a single motor. So this converts the rotational motion into the linear motion. So I use the tuning station to linearly displace the side wall, and that tunes the filter response. So let me just play the video, which is much more interesting. So as the tuning element is linearly displaced, we see that the response of the filter tunes over the tuning range, and the shape of the filter remains same. The insertion loss doesn't change, and the bandwidth also is maintained constant over the tuning range. So we were able to achieve one of the goals, that is to realize the tunable bandpass filter using a single tuning element. Maintaining the constant absolute bandwidth, high Q, insertion loss is pretty good, and around 15% tuning range. So we were able to meet all the desired parameters. And the benefit or the added advantage of the proposed technology, of the proposed design methodology, is that it is scalable. What do we mean by scalable? We demonstrated it for a 5th order bandpass filter. It can be designed for a 10th order bandpass filter or a 12th order bandpass filter with a single tuning element. So the design procedure remains identical. So it doesn't change with the order of the filter. So it is the design methodology is independent of the order of the filter. So we can use a single tuning element to change to realize higher order filters also. And this is the spurious response. And as expected, the spurious response is around 21 gigahertz, which was also verified when we were designing the filter. So we presented this in IMS 2017, and one of the industry came to us and they told, yes, this is good, we can take this in, to our industry, but can you introduce transmission zero? You know industry, right? So industry always helps you to keep a step ahead. So they asked us, this is good, but can you introduce the transmission zero? Because transmission zeros are widely used in the channel payload filters, especially for the satellite communication. So then we explored a dual mode rectangular waveguide cavity filter. Basically, the idea is same. Instead, we used in addition, we use a virtual negative coupling between the resonator 1 and resonator 4 to introduce two symmetric transmission zeros. That's the idea. So we use T101 and T011 modes as denoted by the dotted lines here. And we designed a 4th order filter for proof of concept. So this is how the filter looks like. The input-output coupling is still through the probe. The inter-resonator couplings requires the 45-degree lines. In order to couple these two modes together, we used a 45-degree screw. And then in order to couple between the two cavities, we used rectangular slot for the inter-resonator coupling. And for virtual negative coupling between resonator 1 and resonator 4, we used a circular slot. Their positions, their dimensions can be altered to achieve the required inter-resonator couplings and maintain the constant absolute bandwidth. Basically, this product has to remain constant over the tuning range. And we also shaped the tuning element because we were facing the spurious problem here also, because we were giving an air gap of 0.5 mm on all the sides. And this shaping helped us to push the spurious responses far off. Though there are two tuning elements visible here, it is controlled by a single motor. So they need to be displaced unit with the same distance. So there is a single motor which controls the two tuning elements. So it is basically one independent tuning element. So we built a 4th order Chebyshev filter at 11.5 gigahertz for the payload application with 50 megahertz bandwidth. So we took a very small bandwidth. This was very challenging to do. And we put two transmission zeros, one at plus minus 45 megahertz. So these are the simulated responses. So you can see we have introduced the transmission zeros in the response here, right? So, and we are also maintaining the constant absolute bandwidth over the tuning range. At the same time, we should also maintain the spacing between the transmission zeros should also be constant over the tuning range. We were able to achieve both of them as shown by the graph here. So absolute bandwidth is maintained and the frequency separation between the transmission zeros is also maintained constant. And we were able to meet the payload specifications, that is from 11.4 gigahertz to 12 gigahertz. So we built the filter using aluminum parts. Copper could have been given us much better response, but we went for aluminum because we wanted to do it quickly and prove the concept rapidly. So these are the tuning elements, and this is how we have connected the tuning elements with the nylon spacer. And these spacers are controlled by a single motor, which pulls and pushes these tuning elements within the cavity. So these are the measured responses. And we see that it is maintaining the constant bandwidth over the tuning range, but the insertion loss has increased. You can see there is a rounding off of the insertion loss, right? Because we use the aluminum. And the bandwidth is so tiny that any small machining inaccuracies in the aluminum can significantly increase the insertion loss. And the spacing between the transmission zeros is also maintained constant, and the transmission zeros are not prominent. That is also because of the increased insertion loss effect. However, the concept has been proved. The absolute bandwidth criterion has been is consistent over the tuning range, and the frequency separation between the transmission zero is also consistent over the tuning range. The spurious is pretty good. Generally, the requirement is around 500 megahertz. It is well beyond that, from 11.5 gigahertz to 13 gigahertz. So the next logical step is to, can we introduce bandwidth reconfigurability also? So we proposed a waveguide filter with bandwidth reconfigurability, where we're using two tuning elements. The idea is very much similar to the first idea that we proposed, and where the two tuning elements are linearly displaced. So what happens is the effective location of the single septum within the waveguide changes. So this is the A dimension of the waveguide. And as the two tuning elements are linearly displaced, the effective location of the septum changes. As the septum changes, location of the septum changes, the coupling changes. So the coupling is minimum when the septum is at the center of the waveguide, and the coupling increases as the septum is located at the ends of the waveguide. So with this concept, we propose the bandwidth reconfigurable filter. Basically, we can tune the bandwidth here. And the septum length will give us the... So this is the bandwidth reconfigurable filter. So we can see that the bandwidth reconfiguration is achieved around 40%. So bandwidth can be changed, and the insertion loss remains almost same, or slightly improves with higher bandwidth as expected. And the center frequency is around 13.5 gigahertz. One of the challenge here is, I think some of you might have noticed that if you try to increase the bandwidth, the center frequency doesn't remain constant. Center frequency also shifts. To control that, in order to have a control on the center frequency, we used two tuning elements, one on the left side, another on the right side. Otherwise, a single tuning element would have been sufficient. So we built the filter using aluminum parts, and we used the nylon spacers to connect the tuning element so that there is no electric short between the sidewall and the tuning element. And these are the measured responses. So we got around 35% of the bandwidth tunability at 13.5 gigahertz. So the center frequency is maintained constant over as the bandwidth is reconfigured. Okay, so this was the filters that we developed in the waveguide technology. So when it comes to lower frequency of operation, that is at S band or L band, or sometimes up to C band, generally coaxial technology is widely used. So we also explored the tunability or concept in coaxial technology. So we developed two filters, one using λ/2 resonator post and another using λ/4 resonator post. I will go through them in detail. So conventionally, what is done for coaxial tuning is we use a λ/4 resonator post. This is a coaxial post. This is the outer casing of the coaxial post, and the air gap is linearly displaced. So this air gap, this metallic wall is linearly displaced so that the air gap changes here, which changes this capacitance, and basically change in the capacitance gives rise to change in the resonance frequency. So this is conventionally done. There is no novelty here. No, we didn't add any novelty to this. Instead, what we did was we took an elliptic cavity and used a lambda by 2 resonator post. And the resonator post is rotated within the elliptic cavity. So the same concept happens. So the air gap changes as the post is rotated. The air gap is minimum in this position, and the air gap is maximum in this position because of the axial ratio of the elliptic cavity. As a result, the capacitance changes and then the resonance frequency changes. You can see the resonance frequency change that happens as the angle of rotation is increased. So there are 2 degrees of freedom, the major axis and the minor axis, or the axial ratio and the major axis. By controlling the axial ratio, we can actually have different tuning range. We can go from 3 gigahertz to 2.4 gigahertz, or we can go from 3 gigahertz to 1.6 gigahertz. So the tuning range is within our control. So the added advantage is the Q is twice that of the conventional resonator because the size is double, right? So naturally the Q doubles, and the Q variation is half. This was another benefit of going for the proposed resonator. So how do we go for the inter-resonator coupling? So the inter-resonator coupling basically is also done through elliptic iris opening between the 2 resonators. And there are 2 degrees of freedom, the axis ratio and the major axis. So the axis ratio gives us the constant bandwidth criterion. You can see in the blue curve here, the constant bandwidth criterion, that is the resonance frequency and the product of resonance frequency and the physical coupling coefficient has to be constant. We have seen that earlier. So that is maintained constant over the tuning range as the resonators are rotated within the elliptic cavity. And the major axis itself can control the inter-resonator coupling value. So that's how we were able to achieve different inter-resonator coupling values. Another benefit is it gives us an opening at the center of the filter for the tuning rod to be placed. For the dielectric rod to be placed, it gives us an opening there. So that is another benefit. It gives us a clearance along the axis for tuning rod placement. And for input-output coupling, we used shaped probe. There were a lot of degrees of freedom here, length, width, position, arc lengths, and we were able to meet the constant bandwidth criterion. That is, the reflection group relay has to be constant. So we then assembled the entire filter. Here we didn't face any spurious problem because this works in the TEM mode. So we were not facing the spurious of the waveguide mode coming into the picture. So this is a 4th order filter we have assembled using the input output probes and the elliptic iris openings as the inter-resonator couplings. So as the dielectric rod is rotated, the resonators rotate within the elliptic cavity and hence changes the frequency response. So there is only a single tuning element or the tuning control here, just a single rotatory motion that is required. So the reflection coefficient is also pretty good, better than around 15 dB, 12.5 dB approximately. And the bandwidth variation is also within reasonable. We ensured that with the design of the elliptic iris opening. And the tuning range we obtained was around 30%. So this was pretty good at low frequency. And it is high Q structure, around 5000 at 2.5 gigahertz. So we built the filter using aluminum parts, and we also built the control system using the motor, an Arduino microcontroller, and a driver to drive the motor. We built a simple GUI, and through the GUI, we control the Arduino to shift the motor either rotated clockwise or anti-clockwise. And by doing so, we can tune the filter response. So by controlling the Arduino controls the stepper motor, and the stepper motor rotates the axis of the shaft or the tuning rod, and which tunes the filter response. So you can see that the bandwidth is maintained constant, and the return loss is also maintained constant over the tuning range, and the shape of the filter is also maintained constant. So the rejection criteria can be met with such a filter. Okay. So we were able, these are the measured responses, and this is the measured spurious response. The spurious response as expected will be better than 2f0 because we are using a lambda by 2 resonator post. So the important advantage here is that it uses a single tuning element to tune the filter response. And the bandwidth variation is within plus minus 10%, reasonably constant bandwidth over the tuning range. And there is a reasonably wide tuning range, around 20% in measurement. And if we improve it, we can achieve up to 30%. Once again, the most important feature here is it is scalable. That is, it is in the single tuning element is independent of the filter order. So we demonstrated for a 4th order filter, whereas we can design a 6th order filter or an 8th order filter with a single tuning element and achieve the desired frequency response. So my professor suggested me, why don't we do a tunable diplexer with a single tuning element? So we designed 2 filters, one for the higher band, one for the lower band, and then there is a common tuning element that runs along the axis of both the filters. And by rotating the tuning element, we can obtain the tunable diplexer response. Here there are 2 requirements. One thing, the bandwidth has to be constant over the tuning range. Second thing is the frequency separation between the upper band and the lower band also has to be maintained constant over the tuning range. So it is very hard to do it, but we were able to do it because we've designed 2 filters, one for each of the bands. So one of the feedback was, why can't we make it compact? Because we were using lambda by 2 resonator post, right? We were using lambda by 2 resonator post. So can we do the same thing with a lambda by 4 resonator post? So yes, it can be done. So the idea is simple. So the idea is use a lambda by 4 resonator post and instead use an elliptic tuning element over the post. So as the tuning element is rotated, the air gap changes and hence tunes the resonance frequency. But here there is one catch. There are 2 air gaps and hence there are 2 capacitances in series. So that will effectively reduce the total capacitance change and hence actually limits the tuning range that we can achieve. So we can achieve maximum 15% with this idea, around the tuning range of 15%. For the inter-resonator coupling, we used iris slot opening between the 2 resonators because it is easy to fabricate. And for input-output coupling, we used loop coupling, or we can also use probe coupling, but we used a loop coupling. So the iris structure gives us reasonably good constant bandwidth criterion. This is the iris opening, whereas the loop coupling was not a great choice. We could have gone for the probe coupling instead, but still we went ahead and we fabricated the filter with loop coupling. It is maintaining reasonably constant, but it is not very good. So there is around 15% variation in the reflection loop delay over the tuning range. So these are the simulated response. So the filter tunes. So there is a single tuning element here. So there is a single dielectric rod. As the rod is rotated, all the tuning elements placed on the rod rotate and hence tunes the filter response. So these are the simulated filter response, and we were able to meet the constant bandwidth criterion approximately around plus minus 10% variation. And the insertion loss is also pretty good. So we built the filter using aluminum parts, and we used a commercial plastic for the dielectric rod. And we were able to get reasonably good measured performance, constant bandwidth criterion, reasonably good constant bandwidth criterion, and reasonably good insertion loss. So coming to the conclusion, I have presented frequency reconfigurable filters in both waveguide and coaxial technologies using a single tuning element. So as I mentioned, that was a bottleneck, and we were able to solve that bottleneck. And I have also presented the bandwidth reconfigurable filter with the 2 tuning elements. So these were the publications during my PhD. I have 4 IMS conference papers, including the IMS Best Advanced Paper Award for the coaxial filter that I presented. I have 4 MWCL letters. I have 3 IEEE transactions and 2 US patents granted. Thank you. With that, I complete my presentation. So I open the floor for any discussion or any questions.
Thank you, Gowrish sir, for a wonderful presentation. Here you have covered a brief of your research you have carried out at the University of Waterloo. Starting from the research motivation, literature, and basic architecture, and we ourselves have learned so many things in the filter topologies and the challenges you faced and challenging you have overcome in your research journey. And you have covered the basic topic like how we have achieved the single tuning elements and different topologies like waveguide tunable filters and coaxial based tunable filters. Thank you a lot, sir. You have shared information and we have learned a lot. Sir, before going to the audience, I have one question for you, sir.
Yes, please. Please
yes,
go ahead.
Yes, sir. Sir, here you have shifted the spurious resonance by changing.
So sorry, Abdul, just a
Yes,
second.
sir.
Sorry to interrupt you. So I would like to request to the participants, please do not leave the event, okay? As it is not yet completed, you are going to learn so many things from the question and answer session, okay? So my sincere request to you, please be available. And at the end of the session, we are planning to take a group photograph also. So please stay in the session. Thank you. Yes, Abdul.
Yes, sir.
Thank you.
Yeah, Gowrish sir, I have one question, sir. Yeah.
Yes, please.
Yes,
Yes, please.
sir. Sir, here you have shifted the spurious resonance to 21 gigahertz.
Yes.
Yeah. Yes, sir. Could you please tell me how you have got this idea to shifting?
Yes. So what happened was actually when I had a rectangular slab here. So this slab, if it touches the top wall and the bottom wall, then there won't be any spurious problem. So that will be an ideal rectangular waveguide. But we had to give an air gap of 0.25 mm between the top wall and the bottom wall. So here. So this created the spurious response for us at around 12.2 gigahertz. So then I thought of the idea that came to my mind was I just noted the spurious response shape of the electric fields in the spurious response. Wherever there is a maximum, if you give a tangential, if you make the tangential component of that electric field 0, wherever it is maximum, then that spurious response will be killed. So that's what I did here. So I did the shaping here. So this shaping ensured that the tangential component of the electric field in that spurious mode is forced to 0 by shaping the tuning element. So from there, I was able to push the spurious response to around 21 gigahertz.
Thank you, sir. Now I'm clear.
Thank you.
Yes. Yeah. Now the floor is open for the audience.
Sir, good evening, sir.
Yes, please.
Sir, I'm designing planar filters. So I'm designing how to calculate the coupling coefficient bandpass filter for the bandpass filter.
So coupling coefficient for the bandpass filter, I don't have any slide for that.
Okay.
But I can give you a reference where you can go and there's a detailed reference. There's a very wonderful book by Professor Rafat Mansoor. You can note down this name, and if you Google it, you will be able to get the textbook. Okay. Yeah, you please note down this name. Okay, and if you write the textbook name is Bandpass Filters for Communication System. Tunable is not there, just the bandpass filter for communication system. Okay. So there, chapter number 14 gives you a clear idea of how to calculate the coupling coefficient for a bandpass filter. Yes. So please refer to that particular reference book, and it gives you a step-by-step idea of how to design the filters.
Okay, thank you, sir. Another one question.
Yes, please.
How to decide transmission zeros and reflection zeros? It will be decided or automatically it will be generated while designing?
No, that comes from the specifications. So suppose you have a specification. So let me just open that slide. So depending on the specifications, the rejection criteria will see the specification will give you some return loss requirement and rejection requirement, right? And the bandwidth requirement. So from the rejection criteria, you will get to know the order of the filter. And from the rejection criteria, you will also be able to put the transmission zero locations of the filter.
Okay. Okay. Sir, next, it's a topology source to load. We have 5 resonators. In some topology, first and fourth resonator will be connected. How you can say it should be connected?
Yes. So this topology is inline. It is all pole filter. So there is no cross coupling in this topology. It is a inline coupling, right?
Yes.
So there are no transmission zeros. So if you observe the response of this filter, there are no transmission zeros in this filter. This is an all pole filter.
Yes.
Whereas in the dual mode filter that we have designed, here there is a cross coupling between resonator 1, the mode of the first mode and the fourth mode. This mode, and so the circular slot is what is creating the coupling between the fundamental mode in this direction in this cavity and in this direction in this cavity. So that is creating this virtual negative coupling between the resonator 1 and resonator 4, and that gives us the transmission zero. So if you see the transmission zeros, it gives 2 symmetric transmission zeros will be obtained from that.
Yes, sir. Okay, sir, it's clear, sir. Thank you.
Thank you.
Thank you.
Any other doubts or any discussions or any clarifications? Okay, Abdul, can I take the liberty of reading the chat here?
Yes, sir. Yes, sir. Yes, sir. If you give permission, I will read out for you, sir.
Yeah, it's okay. I will read it out.
Yes.
So it says, as you have been explaining about transmission zeros, could you please give some suggestions on the idea of bringing in transmission zeros for FSS-based bandpass filters? How to improve the sensitivity of such selectivity of such FSS filters? So this is one idea that I'm still working on. FSS filters I have not taken up as a research topic in my research career so far, but I'm planning to work on it. So I do understand how to increase the order of the FSS filters. Probably you will have to use more FSS layers in order to increase the order of the FSS filter. So a single layer will give single order, behaves like a single order filter. 2-layer FSS will behave like a second order filter, and a 3-layer FSS will behave like a third order filter. But then how to include the transmission zeros, that is quite interesting work, and there is a lot of research open in that area also. I have honestly I have not worked on FSS, so but I will take up it as a research area, and surely I will try to contact you in case if I find out any solution for the same. Thank you, Alka, for that question.
Yeah, I hope there are no further questions. Yeah, now.
Yes, please.
Hello, sir. Hello.
Yes, please.
Sir, I have one question. As you are designing this filter for satellite communication, whether the changing the power of the RF power and some mechanical vibration in the payload or satellite will have any effect on the tuning, frequency tuning range or bandwidth tunability in those designs?
Very good question. Very good question. So this question came to us when we were presented this in the IMS, because if you see, we have given an air gap of 0.25 mm here, right? And this air gap actually creates possible mechanical vibration issues, especially during the launch phase. The launch shock is pretty large. But the good thing is, since we are focusing on the payload, so the filter will be off during the launching phase. So the filter will switch on, or the payload turns on only when the satellite is stabilized. So the launching phase vibrations are not going to affect in case of the satellite communication if you use it for the payload as a payload filter. But there is a better concrete solution. The concrete solution is, if you are aware, there are rotary joints used in the satellite communication systems, and the rotary joints also have air gaps. And it is possible to maintain very precise air gap with choke, RF choke, which will ensure the air gap is maintained precisely and is very tolerant for vibration. So if we include an RF choke here, probably I have to include a λ/4 resonator, short the λ/4 resonator, and then extend this path by λ/4 and short it. Then it is possible to make it robust to vibration. It's a very good question. Yes, it is possible to make it robust to vibration.
Okay, sir. Thank you, sir.
Thank you.
Okay, I hope there are no further questions from the audience side. Now, I would like to request Professor Sukamal De to say a few words and a vote of thanks to our invited speaker. Thank you.
Thank you, Abdul, and many thanks to Professor Gowrish. So, am I audible?
Yes, sir, you're audible.
Yeah. Thank you. So, it's a very nice presentation, Gowrish. So, before I convey my vote of thanks, I also do have one or two doubts. May I ask?
Yes, sir. Yes,
in the
please.
forum. Yeah. So it is basically connecting questions what one of the participant asked, that is the vibration effect. So related to that, so you said that you will add one λ/4 line connect. So and then you will connect it to the RF choke, right?
Yes,
so that
sir,
was
yes.
the. So I was just wondering that, see, this is the open end, right? So the open end will become the short end with the λ/4. Correct?
No, I have to add a λ/4 choke with the short end.
Oh, okay. λ/4 choke with a short end.
With a short end.
Okay. Then it makes sense. Okay. And also one more thing. So did you check? However, it's a waveguide-based filter. But did you check the power handling capability of such filters? Sorry if I missed that point during your presentation.
No, we didn't do the measurement on the power handling capacity.
Okay.
But we did notice, we did the simulation and we calculated the power handling capacity of this filter. It turns out to be the same as the waveguide filter. But I will just want to show one limitation of this in terms of power handling. If we see bulk of the electric field is in the waveguide mode, but there is also significant electric field in the air gap between the tuning element and the top plate. So this actually creates the breakdown before the actual resonator breaks down. So if we use a λ/4 choke, then the power handling will be significantly larger.
Okay.
It turns out to be same as that of a waveguide filter, bandpass filter.
Okay. So the approximately that value could be 10 to 15 watt or maybe 20 watt, right?
No, beyond that, much beyond that.
Much beyond that.
Average power will be in terms of kilowatt and the peak power will be in terms of tens of kilowatt.
Okay. So basically the temperature stability will also be improved if we use that kind of technique, right?
Temperature stability, we will have to use different material. Right now we are using aluminum, which will have a large temperature coefficient. So we have to use INVAR or COVAR in order to improve the temperature stability.
Okay. Thank you. That's all from my end, Dr. Gowrish. So thank you so much. So on behalf of IEEE MTTS Student Branch Chapter of IIT Palakkad, so I thank you for taking your time from your schedule and share your thoughts and deeds with us that you did during your PhD time. And it's an excellent work, and the kind of publications or the quality of publication shows that the work has tremendous potentials, not only for the academics, but also for the industry professionals. So thank you very much once again. And on behalf of the society, Kerala chapter IIT Palakkad branch, I would like to felicitate you. And for that, I may need your at-home address so that we can send a memento on behalf of the society of IIT Palakkad. So that I will take it offline maybe after the talk from you. So thank you once again, and have a nice day. And I would like to thank the participants who were there throughout the talk and who listened the talk. I hope that some of you might have benefited from this talk, and hopefully some of you may get some objective of their or the motivations of doing some research on RF filters. So thank you once again to the participants, and also thanks to our team also for organizing such talks. So thank you. Have a nice day.
Thank you, Professor Sukumaran.
Sir, but before leaving, we'll have.
You would like to take a photograph? Yes.
Yeah, I would like to request all the participants, could you please switch on the camera? Photo. Yes, thank you so much.
Take one more time, Abdul.
Yes.
Some of the participants are switching on now. Yeah. Is it done? Or?
Yes, sir, it's done.
Okay, but your camera is off. Okay. Okay. Thank you.
Thank you so much.
Yeah.
Thank you.
Thank you all, and have a nice day. Thank you.